We now know what acids and bases are, at least in terms of some chemical definitions, and in this video we're going to discuss their strength. So our learning goals include learning the identities of some of the strong acids and bases, and then looking at the chemical equilibria that we use to characterize weak acids and bases and their relative strengths. So strong acids and bases, this is going to be pretty simple. A strong acid is basically any acid that is a strong electrolyte. So we throw it into water, it immediately dissociates into H+ ions and the conjugate bases. There are only a few of these that you need to know. They include some of the halo acids like hydrogen chloride, hydrogen bromide, hydrogen iodide. Also include some of the oxy acids, the things like nitric acid, HNO3, sulfuric acid, H2SO4, chloric acid, HClO3, and perchloric acid, which is HClO4. These are really the only acids you need to remember as being strong acids. There are some other strong acids, but they don't come into play very often, and you probably won't see them very much. Strong base, just like a strong acid, is any base that is a strong electrolyte, but in particular a strong electrolyte that is a hydroxide. Now, this is going to be a limited group because, as we learned earlier, hydroxides tend not to be very soluble compounds. They don't dissociate in water very readily. So there's only a few that you'll need to really bear in mind. The first row, these are all of the alkali metal hydroxides: lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, and cesium hydroxide. These all readily dissociate into the alkali metal ion and hydroxide ion. Some that are sort of on the borderline are calcium hydroxide, strontium hydroxide, and barium hydroxide. These are all in the alkaline earth metals, and while these do dissociate to give OH- ions in solution, they're a little bit less soluble than the alkali metal ions, alkali metal hydroxides. Let's talk about weak acids now. And this is a simple definition, but weak acid is basically all the acids that aren't strong acids. So if it wasn't listed there, or you know some other way that it's a strong acid, it is probably a weak acid. Now there's a special equilibrium that we want to pay attention to, and that's the weak acid equilibrium in water. And this is what it looks like. Now we're going to assume that HA is some weak acid. I'm using A as a placeholder because we'll see some examples later on, but this is the general thing that happens. When you put a weak acid into water, what will happen is that to some extent that weak acid will dissociate in the water. It's not a strong electrolyte, but it will dissociate some to form hydronium ions, the H3O+, and the conjugate base, the anion that's attached to the proton at the beginning of the process. So this forms an equilibrium, and this equilibrium can be specified by this equilibrium constant. We have a special symbol that we give these constants. We call them Ka. We use the subscript A to indicate this is a weak acid dissociation constant. So whenever you see the equilibrium constant labeled as Ka, think acid dissociation reaction usually in water, okay? So it would be defined based on what we know about equilibrium constants as the concentration of hydronium ion times the concentration of the anion, the conjugate base, divided by the concentration of the undissociated weak acid. Now remember, this is less than 1, so this does not readily dissociate, so there will always be some of the undissociated weak ion in solution along with the hydronium ions and the conjugate base ions. An example of this would be acetic acid, which is the essential ingredient of vinegar. In this case, CH3COOH is acetic acid, and it undergoes this reaction in water. It forms the acetate ion, CH3CO2-, and the hydronium ion. So its equilibrium constant will look like this, and you can see that the value of this equilibrium constant, 1.8 times 10 to the minus 5, is indeed less than 1, in fact much less than 1, so this is a weak acid. Now, as weak acids go, acetic acid is actually one of the stronger ones, so you can tell that weak acids can be quite weak, but 1.8 times 10 to the minus 5 is the equilibrium constant you would expect for this dissociation. Now let's talk about weak bases. They're very similar to weak acids, although they're bases instead. Weak bases actually include most of the bases that we'll encounter in this course, including all of the organic bases, that is, all of the carbon-containing compounds that are bases. It also includes ammonia, NH3. Now, this also has a weak base equilibrium in water, which looks like this. In this case, I'm going to specify the base as B with a pair of electrons. I want to emphasize those electrons because bases tend to be very good nucleophiles. They have a free pair of electrons that they can donate to create a new bond to a proton. So this is an important feature of bases. In this case, they're going to react with water to grab a proton from water. Water actually serves as the acid in this reaction to form BH plus and then the hydroxide ion. Now the equilibrium constant, again we have a special symbol for this. We call this KB, and it's BH plus times hydroxide ion over the undissociated or the unreacted base forms that KB value. And again, it's going to be less than 1, which means that this reaction goes a little bit to the right, but most of it's on the left-hand side of the reaction. Most of the stuff that you'll find in solution is going to be the base still non-protonated. That BH plus thing, oftentimes we'll refer to it as a protonated base, which is to say we have added a proton to the base. Otherwise, the rest of the base molecule essentially remains the same as it was before the reaction. Now, a good example of this would be phenylethylamine. This is something that is actually found in chocolate, and it has this form when we write it out as a reaction. C6H5, CH2, CH2, NH2, that's phenylethylamine. It reacts with water and it forms the protonated phenylethylamine and the hydroxide ion. So again, here is our Kb value organized the same way as above. This one has a value of 6.8 times 10 to the minus 5, which again is less than 1, which tells us this is not a strong electrolyte, but it does react some in water to form the conjugate acid and the hydroxide ion.